Hi, my name is Brian Toe, and this is my lab report for the Black Hole Modeling Lab. Within the lab, we modeled a star as it orbited a black hole. This was done to estimate the mass of the black hole, compute its net force, as well as the parallel and perpendicular components, respectively, of the F-net. The net force was calculated within the model using Newton's second law, in which net force is equal to dp over dt. I broke this down into its various components, such as solving for the initial momentum and the final momentum, and showing what was plugged in to the model to calculate these values. The black hole's mass was estimated using the force of gravity equation, which is net force equals g, the gravitational constant, times the mass of two objects multiplied by one another. In this case, m1, which is the mass of the star, and m2, the mass of the black hole, and then dividing the whole thing by the magnitude of the position vector between the two objects, in this case the magnitude of the star's position squared. And this was rearranged to solve for m2, which is the black hole's mass, and the black hole's mass as such equals net force times the magnitude of the star's position squared, divided by g, the gravitational constant, times the mass of the star. And this yielded code that looks like such. The seed of our email address was initially plugged in to generate a unique trajectory for the star, which gave us the star's position values over time. And within the code, we edited from line 115 onwards to model this motion for the star, as well as estimate the black hole's mass and calculate the various components of net force. In this case, the perpendicular and the parallel components. This is the code running, and it prints the various mass estimations at each point of motion for the star before printing the final estimation for the mass of the black hole, the magnitude of the net force, the magnitude of the parallel component of the net force, and the perpendicular component of the net force and that's magnitude. And that these values are given here as well. As for the question of what does it mean and how net force and the rate of change of momentum differ, the rate of change of momentum, dp over dt, can be visually seen through changes in the motion, and you can just tell that by looking at it, whereas the net force cannot be visually observed and is instead understood to be the cause of momentum changing. Newton's second law states that the values of net force and the change in momentum are equal, and so dp over dt could be used to solve for net force as it was in this model. As for the what if question of a new black hole being substituted that causes the motion of the star to remain unchanged, the new black hole would be of equal mass because it equal mass to the old black hole because it has the same force on the star and it causes it to go in the same path of motion. Because these things are equal, and because the mass of the star remains unchanged, everything used to calculate the black hole's mass goes unchanged, and so it is impossible for the new black hole to have a different mass than the old black hole. And so the differences are noticeable because they're the same. Possible causes for error in the lab include differences in rounding, which would cause less accurate mass estimations and FNet calculations, as the values used to calculate each are rather large, and even a small rounding error could cause massive variations and differences.